We will be solving this rotation count of a sorted array problem where we need to find the number of rotations that were made to a sorted array. For instance, in this array A, 2 would have been the first element since it is the smallest, and these three elements were brought from the end. That means these three elements were rotated. So our answer will be 3 in this case. But how can we solve this using code? So the first approach that comes to our mind is the basic linear search. We start searching from the leftmost index where we compare the element with the next element present in it, and if this next element is greater, we continue the search, and if it is smaller, then we stop the search since we have our answer. So we will compare 24 and 38. 38 is greater, so it is in sorted order. Then 38 and 40 still sorted, and when we compare 40 and 2, 2 is smaller although it is on the right hand side, so we stop, and our answer is the number of elements that we have searched, that is 3. The time complexity would be big O of n, since in the worst case we'll be searching all these elements till the end. But can we solve it with lesser time complexity? While solving any question, not only this question, but while solving any question, you need to keep in mind that you are using every information that is provided to you. For instance, we are given that it was in sorted array initially. So that means we can somehow apply binary search here because it was sorted earlier. So maybe we can use that property. If you look carefully, you can still find out that it is nothing but a subarray of two sorted arrays. Like if I can plot it like this, from element 2, 3, 9, it is increasing till 23, and same goes for this. So it is nothing but two subarrays joined together. And all we need to do is find the index of the smallest element, because all the elements before that will be our answer. So maybe we can really apply binary search here to do it in log n complexity. But how? Because in simple binary search, what we do, we calculate the mid index and compare it with the target element. But there is no target element here. So what can we actually search for? I will take it to the bottom, and we are applying binary search here, and we will try to figure out as we go. So mid element we can calculate here. It will be mid equal to 0 plus 9 divided by 2, that will be 4. So we'll be taking the floor value and it will be 4. So this will be our mid value. And on this plot here, it is lying somewhere here. So how can we compare this 3 and discard half of the subarray like we do in binary search? I would like you to pause this video here and think for yourself and try to come up with the solution with the information that we have discussed till now. I hope you must have thought about something, and some of you might have got the solution. And if you don't, it's still fine, because now you must have understood the problem in a better way. So let's see what we can do here. So element is this. Now consider that there are only two possibilities, right? Either this mid element, it will be in this first subarray, or the second sorted subarray. There are only two possibilities. Now what we can do, we can compare this third element to the leftmost element of the search space. Now currently the search space is the whole array, so we will compare this element 3 with the element 24, which is here. And since 3, which is on the right hand side, is smaller than an element on the left hand side, that means both 3 and 24 lies in different subarrays, which means that this pivot, I'm calling this pivot, it is just this point where these subarrays are meeting together. So this pivot must lie in between these elements because they both belong to different subarrays. It means we can safely discard all the elements to the right of the mid element. Now, just like in binary search, we were able to eliminate almost half of the subarray. Next, this index was 4. We will again calculate the mid index, which will now be 2 instead of 4. So this is our new pivot. This is our new mid element. We will again compare this 40 with the leftmost side of search space. So 40, which is on right hand side of 24, is greater. That means both of these elements lies in the same subarray. That clearly means we can discard the left hand side because this pivot element or this transition point, it cannot lie in between these elements. So we will discard these elements to the left. Now the left side of search space is 40 and right side of search space is 3. Again we will continue with the binary search here, and this time our mid element will be 3. So this is our mid element and will be index 3. So index 3 is 2. We will compare it with the left hand side element, which is 40. That means again we can discard the right hand side because element on the right is smaller than the element on left. So left sub part we can discard. Now as you can see, the search space has reduced to just 2 elements. That means we can break out of this loop, and whichever element is smaller between 40 and 2, its index will be the pivot index. In this case 2 is smaller, so pivot index will be 0, 1, 2 and 3. 3 is the pivot index, and the number of elements before this index will be our answer. That is also 3. So this is the code here. We will be initializing the left hand side of the search space as 0, right as n-1. Pivot will be initialized to -1. Pivot, I will mention again, it is that index which is the joining point of the two subarrays. You can also consider it as the index of the smallest element. Then we will start the binary search. We will calculate the mid index. We will compare the mid element with the leftmost element of the search space. And again, if the leftmost element of search space is greater than the mid element, that means both of these lies on different subarrays. For example, mid was lying initially here and the leftmost element was here, and since a right element is smaller than the leftmost element, they are lying in different subarrays. So this pivot element must also lie in between, so we were discarding this right part. So we will update the right equal to mid. Also, if both of these mid element and left were lying in same subarray, this condition would have failed and we would have moved on to this condition. Now here we are comparing mid with the rightmost element of search space, and if a mid is greater than a right, we were discarding the leftmost part. Here you can visualize it as if mid was lying here, this is the mid element, and rightmost element is consider it can be here or maybe here, anywhere in the second subarray, then it would have been smaller than the a mid. So this condition would have failed. This condition would have been true. So we could have discarded the leftmost part because pivot cannot lie in here. And then in a similar manner, we would have continued this process until the search space, until the difference between right and left is greater than 1. Now you must be wondering when we will be using this condition, this third condition. It is just to cover a corner case. Suppose this array was completely sorted and there was 0 rotation, or the rotations were multiple of 10. In that case, if we would have plotted a graph, the elements would have been continuously increasing since number of rotations are 0 or multiple of the size of this array. In that case, both of these conditions would have failed. You can verify it yourself. Mid would have lied somewhere here and both of these conditions would have failed. In that case, we can easily say that whole subarray is sorted. and we can make this the pivot element, and we can easily break out of the loop. Complete code of our program, and you can see here this pivot thing is here. If the search space size has reduced to 2 elements, in that case pivot would still be our initialized value, that is -1. So whichever element is smaller, we will assign that the pivot. So if left side element is smaller, we will make it the pivot, and if otherwise, we will make the right side of the element as pivot and we will print it. So we have already seen how to solve this problem when all the elements are distinct. But now let's see what happens when duplicate elements are allowed. We have this array A here, and again you can draw a graph for this, and 1, 2, this increases, and this remains same for 3, and at the same height approximately I will draw this, and again it's same, it's decreasing again. Now let's try to apply the same procedure that we did earlier. So I've just copied this code from the previous slides, and now again we will find the mid element, which in this case will be 4. 0 plus 9 divided by 2. I will write it down. Mid equal to 0 plus 9 divided by 2, and we will be taking the floor value, so index 4. Index 4 is our element 3. So this will be our new mid element. Now if we compare this mid element with the leftmost element, then it is equal. So this condition won't be true. Then we will compare this element 3 with the rightmost element of the search space. Again, this condition will be false. And if we execute this else part, then obviously we will get wrong answers because it's not true. And there is no problem with the code. Actually, we cannot apply binary search here because there is no way for us to distinguish between any 3 which is present this side or a 3 which is present on this side. While applying binary search, we cannot distinguish whether any 3 present here, whether the pivot is in the left part of this 3 or on the right part. So all we can do is do a linear search to find out the number of rotations, and hence the time complexity in this case will be big of n only.